like this, where we will do some experiments. And there are also one kit. So mainly these are kit based. So another setup for fiber amplifier. Okay. Then there are some systems where the softwares are installed. Softwares related to optical fiber or optical systems, optical communication. Then there is one kit, that is Manchester coding and decoding kit. And is another kit, that is TDM, time division multiplexing digital. Then this is another kit, time division multiplexing analog. So there are some arrangements where fiber attenuation is calculated, and the attenuation and some experiments are there to calculate numerical aperture. This setup, okay, numerical aperture we will calculate. And this setup is for the first experiment, that is fiber optic analog link and fiber optics digital link. Okay. So here you go through the manual. So here I am showing you the manual, the same one that is uploaded over there. So it is fiber optic analog link. So what is the objective of this experiment? Is to study a 660 nanometer or 990 nanometer fiber optic analog link. In this experiment, you will study the relationship between the input signal and received signal. So here two wavelengths are mentioned, 660, another is 950 nanometers. So what is the difference between these two? 660 nanometer and 950 nanometer. What is the difference? How you will characterize this?
So they are from different generations.
That's true. Source is different. But what property distinguishes them in terms of light? Wavelength is different. What is the basic difference? What is the visible spectrum range? What is the visible spectrum range?
So it's 400 nanometers to 700 nanometers.
700 nanometers. So out of that two wavelengths, 660 and 950. Can you see what is the difference now?
Yes, sir. We can see the 661, not the 991.
Yes. So 950 falls in the infrared region. Okay. You cannot see it, it is not visible. But 660, it is generally red light wavelength. Okay. You can see it. So that I will show you now. Okay. You see in this kit, this is the kit where light source is, okay, let me ये फुल मोड होगा तो हमको भी दिख नहीं रहा है फुल मोड. अच्छा. Are you see the? Do you see the screen? What I am showing?
Sir, you are showing CRO screen, sir.
Okay, okay. That means
Partial
uh,
CRO is there, sir, but the other
no,
kit is
okay, no. I thought that uh, to show you I need to share the screen, but for mobile it is not required that one. Okay. So sharing, yes. If I share the video now, then it will come in full mode. So is the screen now increased? Screen size?
no, sir. It's the same, sir.
Is the same size?
Yes, sir.
Okay. Then from my side, it is better, uh, better
Yes, sir. It is lagging here.
visual.
That better, sir.
Huh?
It is lagging now, sir. Yours was better, sir. Internet speed, like.
Okay, now I will show this. You see that there are two light source. These are two light source. One is 660 nanometer. Inside this, some from inside light is coming out. This red light, LED, and this is the optical fiber. Okay, this is the optical fiber, and it is basically a plastic fiber made from plastic material, and it is multi-mode fiber. Okay. So now it is now connected to one photo detector. Okay. And you see the companies. What is written there? Brand. What is this?
Sir, Infineon.
Infineon. So this is popular company, yes, isn't it? This Infineon comes to our campus for placement. The semiconductor company. So this LED is 660 nanometer, and another is 950 nanometer wavelength source. And you see, this is another semiconductor detector, photo detector. There are two. So two transmitter, two receiver, two light source, two photo detectors. So we'll use one any of them. Right now we will use the 660 nanometer wavelength. Okay. Now I'll just take out the fiber from the photo detector so that you can see what is coming out of the fiber. Okay. So you see that this is a light coming out of the fiber. Okay. Do you see it?
Yes, sir.
Okay. So it look better if you directly physically if you see it, but from mobile is not that much visible, but still you can experience it. So now here what is there, that is light source is generating light and it is going through this optical fiber, okay, and coming out of it, and we should not touch the fiber tip because dust particle may go inside, so it can block the light. And also if it is silica fiber, then you should be careful because Silica, you know, it is harmful for your body, skin. So I have inserted here. I've connected, place the fiber inside that one. Okay. Now what things we need to do? You all please keep one pen and paper, or pencil and paper. Okay, so that you can record the readings. You can record the readings. So uh, you see the first block diagram connection or experimental setup for this is that first we will transmit the analog signal, and then we'll transmit to some buffer stage. Buffer stage is nothing but it matches the impedance between the input circuit and the output circuit. Okay, and then some circuit, that is transmitter circuit, is used. Okay, and here after that it is showing that light is going out. That means it is an LED. And after that it goes through optical fiber. Fiber cable is there that I have shown you, and then detectors. After the detector, we need to use some amplifier circuit. This amplifier circuit. Okay. So this is basically because the photodetector output is very low. Okay. So we use transimpedance amplifier because we need to convert the current into voltage. Transimpedance amplifier is used to convert current into voltage. You know that current is the what? It is the detected current. So that is basically due to the flow of photocarriers. That is charge that is generated due to the photons. Okay. When photon falls on photodetector and photodetector is reverse biased, then it electron hole pairs generated. And earlier I told you that how electron and hole pair is generated. So one electron that is staying in valence band that goes in the conduction band. So leaving one hole in the valence band. So in that generates the photocarriers. That is called photocarriers. Now the reason of making the photodetector reverse biased is because you have to keep the electrons or charge carriers in valence band. That means at lower energy level. लोअर एनर्जी लेवल में बैलेंस इफ यू रिवर्स बायस रखोगे तो इलेक्ट्रॉन्स बैलेंस बैंड में रहेगा और इलेक्ट्रॉन्स जब फोटोन पड़ेगा उसके ऊपर तब वो इलेक्ट्रॉन्स ऊपर चला जाएगा कंडक्शन बैंड में और इलेक्ट्रॉन होल पेयर जनरेट होगा और अगर कोई सर्किट क्लोज सर्किट रहेगा आउटपुट में तो वो इलेक्ट्रॉन होल पेयर फ्लो करेगा. ओके. So now output may load resistance, so that current is actually very low because it depends on number of photons incident. So the current is very weak in nature, and along with that many types of noises are present. In internal noises are present in photodetector. So you have to amplify the current, so you need to use some amplifier. But you have to get it in the form of voltage. So you need to use impedance amplifier. Transimpedance because it is the input is current, output is voltage. So voltage by current is resistance or impedance, and trans means transfer. So one parameter is at two parameters are at different side. One is at output, another is input. So that's why it is called transimpedance. So now that output, at the output you just get the analog signal. Okay. So this thing we have to observe what kind of analog signal is coming, and you will vary the input frequency, okay, and record the record for different input frequencies, so that bandwidth so that you can draw the frequency response graph. Frequency response graph tells you the gain versus frequency. So in that gain versus frequency, gain is what? Output voltage by input voltage. The input voltage is your in that voltage you have applied at the transmitter side. That is before the optical pass, before passing to optical fiber at the transmitter circuit. That is the input voltage, that is constant. So I have kept that input voltage 2 volt peak to peak. That I will show you now why it is called 2 volt. Why it is 2 volts? You can see here. I am just connecting it to 2 volt. So here input हम लोग फंक्शन जनरेटर से दे रहे हैं, कहीं से भी दे सकते हैं, इनपुट फंक्शन जनरेटर से दे रहे हैं। अभी एनालॉग आउटपुट में कनेक्ट किए, फिर यहाँ से आया, ठीक है, और हम अभी जस्ट इनपुट को देख रहे हैं सीआर में। सो इट इज सीआर इज इनपुट वोल्टेज 500 millivolts, that is size of one block. So 1, 2, 3, 4. Total 4 blocks is there. So input is near about. You can slightly increase to make it to 2 volt. Just I'm increasing now. So now it is fixed to 2 volt. So you just note down the input voltage. Okay. Then we'll see the output. So see the connection, that input frequency is applied at this point. Analog buffer is going analog output, then it is going directly to the transmitter circuit, transmitter in. There are some settings of the jumper. So we have kept it the supply voltage of transistor 12 volt. Okay. And then we have used transmitter 1. So we use this jumper. This jumper, it is for transmitter 1. And then it is going through optical fiber. Okay. Then to photo detector. And photo detector, this is a receiver circuit where input is internally given and transimpedance amplifier is there, and at the output you see analog output. This is the analog output. So this analog output, I am taking this and applying to CRO. Okay. So you see the output voltage is how much? It is now slightly reduced. Obviously it is going through different stage and optical fiber. Okay, so and also trans amplifier is used. So now it is almost near about 1 volt. Okay. So 500 millivolt, 500 millivolt, 1 volt, slightly greater. So now here you see that you have kept the frequency near about 1 kilohertz. So now you start taking the reading. So first, let us keep it to 250 hertz or 200 hertz. So I have kept it to 200 hertz input frequency, and you see the output voltage. It is 2 volt peak to peak, 1 volt peak to peak. The input voltage was 2 volt peak to peak. You note down, and output voltage is 1 volt peak to peak. This is for 200 hertz. Then we go for 500 hertz. So there also you see for 500 hertz output, it is 1 volt peak to peak. Okay. Then we go for, so at lower frequencies it will remain almost same, but if you go for higher frequencies, attenuation will start. So that is because the use of electronics, not because of fibers. Since you are use electronics, that is at transmitter, you are using transmitter circuit electronics. There are also BJT and PN junction. Okay. Then at the output also you are using transistors or amplifier op amp. They are having frequency response or bandwidth gets limited. So anyhow, the we will see the response of the overall link, analog link, not the particularly the optical fibers. Okay. So for overall fiber optic analog link, we will calculate the bandwidth. So now we'll see for, let us say for 5 kilohertz. Okay. So note down the readings for 5 kilohertz. Are you noting down?
Yes, sir.
So lastly, you have to show me when all the readings will be taken. You have to show me the overall results. Okay. I am not noting down the results, but I know the final reading. So now it is set to 5 kilohertz. Okay. So 5 kilohertz, and you see what is the voltage. So there also, how much voltage can you tell?
Yes, sir. Sir, 1 volt peak to peak.
1 volt peak to peak, correct. So now we'll go slightly higher frequency, let us say 100 kilohertz. So now I set to 100 kilohertz. So it is 100 kilohertz. Now here it is. I have to adjust the scale, time scale. There also you see 1 volt peak to peak, okay, at the output. So now I'll directly go to 100 kilowatt. After that, say it is 500 kilowatts. Five hundred kilowatts. 497 or 500. Let us keep it. 500 kilowatts. Then you see the response. The response has started to decrease. Okay. So you note down the readings.
Sir, excuse me, sir, it's not clear the CRO readings.
No. I am adjusting now. Just wait. So, okay, you see that some distortion is there in the output waveform, okay, but still you can take the magnitude. Okay, so magnitude is in this case now reduced, and you can see the magnitude near about 15. Okay, 500. Earlier it was how much?
Sir, 1 volt peak to peak it was earlier.
1 volt peak to peak. Okay, so I have changed. Okay, just you wait. You have to change because I have changed the settings. So for lower frequency, it will slightly increase. Okay, input is 2 volts. Just you change all the readings by yeah, this one. Okay, so 1 volt. Now it is coming 3 volt. 3 volt. So what is the input? एक बार check करते हैं. इसको पकड़िए. इनपुट कितना दिए हैं, एक बार check. 2 volt रखना. इनपुट से within this range, you will be getting the frequencies, that is bandwidths, two bandwidths. One is electrical bandwidth, another is optical bandwidth. For optical bandwidth, the electrical bandwidth, it will be 1 by root 2. That means 0.7 of the maximum voltage. So if it is 3 volt, then 3 volt peak to peak, then 3 into 0.7, it is 2.1. So 0.707, 0.707 to 3, it is 3.1, 2.1 around, 2.1 volt. So note, so you have, so that frequency will be the electrical bandwidth, and for optical bandwidth, you have to calculate the frequency at which the power, optical power, is halved. That means optical power is directly proportional to voltage. So that's why optical power would be the frequency at which voltage is halved from the maximum value. So if maximum value is 3, then optical frequency will come around the frequency at which voltage is 1.5, that is 50%. And in electrical case, it is 0.7, 70%, 70.7%. So these are the readings for the analog case, okay, analog signals. Have you understood?
Yes, sir.
You just show your readings, Harshvardhan. What I have told, just show your readings.
Sir, can I read out the readings?
Yes, yes.
Sir, for 200 hertz, sir, we got 3 volts peak to peak.
Yes.
For 500 hertz also, we got 3 volts peak to peak. Similarly, for 100 kilohertz, for 5 kilohertz, we got 3 volts peak to peak. For 100 kilohertz, 3 volts peak to peak. For 500 kilohertz, 1 volt peak to peak. And for 200 kilohertz, 2.5 volts peak to peak.
Yes. So 200 kilohertz will come before 500 kilohertz.
Yes, sir.
Yes.
Yes.
So when we'll take the finally, we'll take the right in the table. So 200 will come before 500. So that way you have to make the readings in semi-log graph paper. Okay. Semi-log is required for more number of readings and for larger frequency range. So, but I think here also we have covered frequencies for more range. So semi-log will also be required in this case. So you have to plot the data in semi-log graph paper, and from there you have to get the two bandwidth, one electrical bandwidth, another is optical bandwidth. Okay. So now next we will try to show you the digital the waveforms. Okay. So in the manual you see that for the fiber optic digital link, there are also same circuits are required, but in digital case it will be slightly modified. The precision circuit is required, and you have to take the readings for different waveform. You see in the manual what is written. Okay. So the input signal, whatever the input signals frequency, you have to draw input signal, and also you have to draw the output signal or detected signal. This thing you have to do for few frequencies, 4 frequencies. Let us say 1 kilohertz, then 10 kilohertz, then 100 kilohertz, then 500 kilohertz. So for square wave, high frequency generally do not come very good. So let us keep it for means the square wave generator, TTL signal generator is not very good for high frequencies. So let us keep it 1 kilohertz, then 5 kilohertz, then 50 kilohertz and 100 kilohertz. These 4 readings I will show you. 1 kilohertz, 5 kilohertz, 50 kilohertz and 100 kilohertz. So I will switch to the TTL waveform, okay? TTL signal and चेंज तो करना होगा, देखना चाह रहे कैसा आ रहा है। ये देखिए ये वाला, अब देखिए TTL आ रहा है कि नहीं आ रहा है। TTL स्क्वायर वेव आ रहा है, ठीक है। स्क्वायर वेव फिर इसमें यहाँ पे डिजिटल बफर में दीजिए, अभी डिजिटल बफर में कनेक्ट करना होगा। पे भी आ रहा है सिग्नल, पे भी आ रहा है ट्रांसमीटर में। यहाँ पे कहाँ आ रहा है TTL, ये वाला है। हाँ तो नहीं दोनों केस में ही आना चाहिए। ये इसका दूसरा किट कहाँ है, उसमें कीजिए ना, ये किट थोड़ा गड़बड़ लग रहा है। लाइए उसको लाइए। अभी नहीं दीजिए, छोड़ दीजिए, ये आ रहा है देखिए 5 वोल्ट में आ रहा है। ये देखो अभी क्या हो रहा है, यहाँ पे हम लोग यहाँ पे तो यहाँ पे हम लोग इनपुट सिग्नल दिए square wave. So that square wave is, you can see it is coming square wave is direct input signal. Okay. If you slightly reduce the frequency, let us say I keep I have kept it to 1 kilohertz, and that time this is the input signal. Okay, 1 kilohertz frequency. Okay, so pure square wave you can see. And what is the output in that case? Okay, you just observe that You see, this is the output is coming. I have connected the point here. Okay, the same circuit, and this is the output wave. So you just note down the output waveform. That is 1 kilohertz signal. Okay, and voltage is 2 volt peak to peak. Not exactly 2 volt, it is slightly lesser. Let us say it is 500, so it is near about 1.5. Okay, 1.5 volt peak to peak for 1 kilohertz signal. Now I change the frequency to what frequency I told you?
Sir, 5 kilohertz.
5 kilohertz. So this 5 kilohertz I have set it, and you see the output waveform. Here also we get 5 kilohertz signal. You can see here in this CR, very good CR. It is DSO, digital square oscilloscope. Okay. So 5 kilohertz signal, and also peak to peak is 1.5 volt. Peak to peak voltage. Then next frequency I told you 50 kilohertz. इससे कम तो नहीं हो रहा है. 50 kilohertz, 50.5 or 50 kilohertz. Let us say it is 50. So here also you'll see it is 50 point something, same frequency, and here also peak to peak you note down it is 1.5 volt. Okay. The next reading is I told you that let us keep it 100 kilohertz. So it is 100 kilohertz. Then also you will see the peak to peak is slightly lesser than, yeah, it's okay. So it is 1.5 volt, and frequency is 100 kilohertz near about. So these are the 4 readings and waveform you have to draw.
Sir, what is the input voltage, sir?
Input voltage is 5 volt.
5 volt.
That is
Yes.
TTL signal. TTL signal is 5 volt always, 5 volt peak to peak, and here input voltage is decreasing, okay, because here we are not passing it through amplifier, and there at the output stage amplifier circuit is used, and maybe may have some distortion. Okay, we'll see later on, but whatever it is, for analog case you have no need to means plot the readings with gain, just plot the output voltage with frequency. Okay. So now today you have finished the first experiment. So in the next day we'll do the next experiment. Anything you want to discuss? Anything you want to tell?
No, sir.
Okay. So you have to make the lab manual. Okay. And I will give you the assignment. You have to write the you have to make the lab journal. Okay, you write on your own handwriting. Okay, draw the whatever we have discussed. Okay, as per your uh, suitability or whatever the things are that are given in your manual, you make one lab journal of 3 to 4 page. Okay, and containing the graph papers, observation table and graph papers.
Sir, you're not audible for some time, sir.
Okay.
Sir,
So
once
make
again,
your
can
lab journal. You have to make your lab journal. Okay. So, that is based on the theory and circuit diagram. First, there will be aim, then theory, then circuit, experimental setup, then graphs, observation table, etc. You have to write down. No need to direct writing this or copying everything from manual. You just study it and you just write it some main points. Okay, whatever you feel like, you just mentions your lab journal and submit it by the next week. I will give you in the assignment form.
yes, sir.
Clear?
Sir,
Okay.
the in the second experiment, the graphs we can do normally, no, sir. Those square waveforms we can do it normally,
Yes,
right?
yes.
Yes, sir.
Yes, yes, that is second normal graph. Where you have to draw the observation table, okay, and the experimental setup, graphs. These are very important. Also theory, okay, theory and this apparatus required. You just study the lab manual first, then you write, okay, then we will see it. So I hope we will meet in offline mode in the by the next week. We are expecting you to come here. We are waiting for you. Don't delay. Okay. Okay. Then I am closing here.